This is a 1.5 volt battery, D-sized or 𝗟𝗶 sized. This one is, well, long since expired, March 2021, and yet we still use them. These particular ones we're using are from 𝗟𝗶H. Other brands do exist. We need to know that so that we can look up what we expect the internal resistance in EMF to be for one of these from the data sheet. So that's why we have to know what the brand is. We'll use a bank of them. We'll use 4 of them connected in series with each other. A variable resistor, rheostat style, but we use a variable resistor. Bunch of leads, crocodile clips, a switch, ammeter and voltmeter. We use these multimeters, and of course the old lab book to write stuff down in. Now before I start, I'm going to use my favourite search engine, other search engines are available, to look up what I expect the internal resistance to be. I mean, the EMF I'm assuming is going to be 1.5 volts, but we're going to look up what we expect it to be for one of these. So, a quick bit of Googling. Internal resistance of, oh there we are, that 𝗟𝗶H Industrial D. Hey, that looks familiar. That's exactly what I've got here. Look at that. Let's go ahead and click that, the first link, and it might have the information in. It might not, of course. A bit of whirring and clicking. And here's a website, 𝗟𝗶H_battery.co.uk. And, well, we don't have internal resistance listed, but we do have impedance listed. And that's listed as 136 milliohms at 1000 hertz. Well, the impedance is the internal resistance plus the reactance. The reactance depends on the frequency, excuse me, the frequency of AC, whereas the internal resistance doesn't. So this is sort of an upper bound. If we add the internal resistance to the reactance, we get this. So the internal resistance will be something less than this. This gives us an upper bound value. We'll go into the data sheet. There might be some better details in there. Let's just open up the PDF. And of course, we can reference this by the URL we downloaded it. Okay, the picture looks slightly different, but it's probably the same thing. LR20, so it's the same size battery. PC1300. Can I see the code PC1300 anywhere on here? No, I can't, so it might not be the same battery, but it's showed the same picture before, just not now. We've got our impedance here of 133 milliohms. Remember, that is the internal resistance plus the reactance. There's nothing there that tells me what the internal resistance is. Although it is interesting, these graphs do show how the terminal potential difference is going to reduce over time when we have constant current passing through our battery, when we have a constant resistance across our battery, or a constant power being delivered by our battery. And that's interesting or not. I mean, these batteries are quite out of date now, so, you know, March 2021, so we're probably going to be down here somewhere on the graph that have been used quite a lot. But we'll see what comes out. I found this data sheet, which even looks exactly the same in the picture now, and this one is going with 136 milliohms of impedance. Remember, that is the internal resistance plus the reactance, which whatever that is. So I put the term internal resistance in quotes just to see if I could get some figure for the internal resistance, not just the impedance. And obviously we've got some nonsense that the internet gives out as well. But then we've got, you know, battery specialties down here. We click on this. That's not the same battery. It doesn't look the same. Same size. This claims to be a D-size battery, 𝗟𝗶H, same brand. Possibly not the same electrochemistry inside. Difficult to tell, but if we scroll all the way down to here, there's a 𝗟𝗶H alkaline technical bulletin. Well, this does claim to be an alkaline battery, So Duracell alkaline battery, it's maybe as good as we're going to get. And if we search inside this document for internal resistance, or just the word internal, there's a whole section on it. It says general characteristics low. Can't do very much with low internal resistance. I need a number. We keep going. It tells you some information about how the battery works. And then internal resistance, alkaline cells, because of their compact construction, highly conductive electrolyte, have low internal resistance, usually less than 1 ohm. So now we've got a number, less than an ohm. Well, 136 milliohms, which was the impedance of this, that's definitely less than 1 ohm. Have low internal resistance characteristics as a benefit for blah, 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 and it talks more nonsense. There are some more references to it. One more reference to it, right at the bottom, applications. So we can reference this and say that we're expecting a number less than 1 milliohm. We can do that. I don't think any of these graphs have internal resistance on them that we can read off. No, nothing like that. They're all to do with load resistance. And we've seen those sorts of things before. Yeah, different modes of discharge. So we're going to have to go with 1 ohm internal resistance or less. And if we get something down in the order of, so say, 136 milliohms for each of these, well, then we'll be happy. So we can reference this later. Now, it may seem a bit peculiar trying to find a reference for the internal resistance before we've even started, but there's a good reason for that. If there was no way we could possibly find any reference for this, then how would we know if the amount we measured, the internal resistance we measured, was sensible? So it's always a good idea to think in advance. How will I know whether my result is correct? How will I know if my result is accurate? Well, to find out, I need to be able to reference something. Well, I now have a ballpark figure. It might be the best I can get. I might be able to Google around a bit more later, but it gives us an idea. So, measuring internal resistance of a battery. I don't want to get into a fuss about whether this is a cell or a battery. Now, you're in key stage 2, key stage 3. You get all excited about the difference between a cell and a battery, and you get told, oh yes, this is a cell, but that's a battery of cells. Ooh, and you get all excited about that sort of thing. But then I don't know what the internal structure of this is. The picture showed it with a single anode down the middle. It's possible that it's got multiple cells within each of these, in which case this would truly be a battery. Well, I don't know. So I'm just going to use the colloquial word battery to describe this thing. And after all, that is how it describes itself, as a battery. So that's what I'm going to call this. There's a place to argue about that sort of thing. I don't think this is it. So let's draw a quick sketch of our circuit diagram before we start with anything else. I'm not going to use a ruler, perhaps I should, but I'm just going to do a quick sketch. What we're going to have is our battery of cells, like this, whatever that means. And I'm going to connect across that a load resistor, just like that. In series with the load resistor, I'm going to put an ammeter, and I will connect a voltmeter across the terminals of my power supply, my battery. But the battery has an internal resistor, which I'm going to represent as a single resistor here. Now, I know that this is in fact 4 batteries, and so the EMF that I measure will actually be 4 times the EMF, and the internal resistance I measure will be 4 times the internal resistance, because these are in series. So I can correct that later just by dividing my EMF and dividing my internal resistance by 4. But for now, let's just stick with this, and we can do that simple step at the end. So what I've got here is within this dotted box here, that is actually my box here. They're the terminals for it. So I want to connect a voltmeter in parallel with my power supply, just like that. Let's call some terms. Let's call this the load resistor, or load resistance, R. This is the lowercase r for the internal resistance. We've got V, that would be the potential difference measured across the terminals, or the terminal PD. And we can use the usual epsilon for EMF. So what I get out of the terminals, the V I get out of the terminals, is going to be equal to the EMF subtract whatever potential difference is dropped across this internal resistor. Well, assuming that assuming that the voltmeter has infinite resistance, and the digital meters have got pretty high resistance, so that's not terrible, millions of ohms. So if we say that's got infinite resistance, then as a fraction of the current, almost no current's going to pass through it. So we can say that the ammeter here will also measure the current that passes through the internal resistance to as many significant figures as I can measure. So the potential difference across the internal resistor is the current through the internal resistor multiplied by its resistance. Now, you look at this equation, you can see that we have got two constants. We've got the EMF, and we have got the internal resistance. Now, over time, the internal resistance will increase because there is a chemical reaction taking place. It's going to make the electrodes have a smaller area. It's going to put our, reaction product in here as well, which is going to impede the flow of ions. So the internal resistance of this is going to increase over time, but as long as we do the experiment over a short period of time, it shouldn't matter. We can say that internal resistance is constant. We can say the EMF is constant. So our variables are our current and our load terminal potential difference. Now, of these, which one of these is our independent variable, the one that we are going to have control over, the one that we will exert our will upon? That will actually be the current. We're going to use this rheostat as a variable resistor connected across the, hole in my book now, connected from here, this one here, down to this one here. We're going to use this to change the current that passes through our battery of cells. So that's actually going to be our independent variable, and our dependent variable will be the V, the terminal potential difference measured across this thing, which will depend on the internal resistance of this thing. Now, I have got a load resistor R. I don't actually care what that value is. I don't have to measure the resistance of this thing. I don't care. It's not part of my equation. So my table of results is just going to have my independent variable I, measured in amperes, and my dependent variable V, measured in, I'll put volts, I might have to slip a little million here. Actually, I won't for this, it'll be volts definitely. Amperes, I might have to slip a little million here or something. We'll see. We'll leave it like that for now. And that will be my table. I don't need a column over here saying what proportion of the way through this I am. I can't take repeats because I'm never going to be able to get exactly the same current in order to measure exactly the same potential difference, even if I were to place this in exactly the same position. Small differences in room temperature are going to have an effect, and so the current will also be different. So there's no point me adding repeats on here. It's just meaningless to do so. So this could be quite a quick practical. Let's rig up the circuit. Yeah, it's quick practical, but don't worry, I'll make it take ages. Oops, crocodile clips. Onto the top of our battery like that. So I'm just going to check that these batteries aren't completely dead before we start. Really, we should be using fresh batteries with this. Really should be using fresh batteries. I'm not. I'm using these old knackered ones. It's fine. Okay. That is considerably lower than I would have wanted. Hello, it's wobbling all over the place. That is considerably lower than I would have wanted it to be. Yeah, I got 4 1.5 volt batteries. Now, I'm no expert in mathematics, but 4 times 1.5 is 6. And that says 3. How knackered are these batteries? I might have to go and swap them out for some... Supposed to be 1.5 volts. Yeah, I can't use these batteries. I just can't use them. I'll be back in a moment. All right, let's try that again. These are some, let's not call them newer batteries because they still expired in March 2021. But when I connect my voltmeter across them, I get about 1.4 volts, should be about 1.5 volts. So they are a lot healthier. Yeah, about 1.4 volts. So I could use these. Yeah, note to self, I need to order some more batteries before the students do this practical. Let's just have a look. 1.4 volts, they're enough. They're all about the same. So I think this is about as good as we're going to get. I have got some of another brand, which are slightly newer, I think. What's the expiry date on these? These are mercury, cadmium, alkaline batteries. I might be able to look up the reference for these. These are oh, there we are, 2022. So these are slightly newer, still out of date. Let's have a look. 1.475. So these are actually better. So I wonder whether it would be better for me to use these batteries, even though it's a different brand to these. I could look up the data sheet for these later instead. So let's use these instead. And worst case scenario, these say alkaline, these say alkaline. They're probably very similar, although they will be different because of brands and corporate secrets and stuff. But they will be very similar chemistries, so I could expect very similar internal resistances. So worst case scenario, I'll say, we've got a vague idea of it should be less than an ohm for internal resistance. So I reckon less than 4 ohms for this. We could just use this battery pack. So here we go. Let's connect it up just to double check we're getting nearly 6 volts. 5.72 volts. It's okay, that's pretty good. Connected the wrong way around, but that's not the end of the world. Right, okay, let's connect up our circuit. So I've got my leads with my crocodile clips, which I can connect to the top and bottom of this pack there. That's the negative connection, that's the positive one. Let's take the positive one. I'm just going to follow this one round. Stick it into a simple push switch. I'm going to use that because I don't want everything to heat up. Higher temperature conductors have more resistance if they're positive temperature coefficients. So I don't want to have higher internal resistance just because the batteries have warmed up. So that switch should reduce that effect. This is all about trying to control my control variable, which is R. And I could write this down, controlling R by using a switch to prevent the temperature of the battery increasing. Connect that to an ammeter, so let's use this as my ammeter, stick it on the 10A setting. This was positive, that was negative. Let's just do a quick check. Wow, so with no resistance other than the internal resistance, we get a whopping 2.39 and dropping current. The current's dropping, of course, because the internal resistor was increasing in temperature. Then I need my voltmeter. So let's get this meter here. Put that on the right of the ammeter. That's going to be my voltmeter. Positive one connected straight across the positive terminal, negative one across the negative terminal, just like that. That's our EMF there, because there's no current flowing, or something close to it. We, of course, have not connected our internal resistor yet, so let's better get that connected as well. So let's disconnect the ammeter, which is the one on the left, connect that into my variable resistor, out of the other side of my variable resistor into the ammeter. So now I have an internal resistance that I can, an external resistance, a load resistance that I can change. Super duper, I've got a spare lead here, that's everything that I need to do. So let's go back to the lab book and let's start recording data. Before I start, I might just make a little note of those variables. So I might make a note here and say that, what does I say, 22 volts. No, that's not where, oh, it's a dodgy switch somewhere, look at that. Right, let's just make a little note here and say control variable. I'll just write that stuff down. There we go, I could probably have worded it better. Control variable, internal resistance used, internal resistance, full stop, capital U, use switch to prevent batteries increasing temperature. And I could have made a thing there about positive temperature coefficient or something. It doesn't really matter. I've got the idea there. Right, let's get some data recorded. Pop this under here. I might as well do it in real time because this is not going to take long to gather the data. Got these wires out the way so that you can see the screen as well, so that you can play along at home. Okay, so press the switch. We've got 0.48458. So 0.48458, 4.58. That's what we had there, I think. Near enough. And you have to go fast because as current flows through the battery, the temperature of the battery is going to increase. It's going to increase the terminal resistance, which is going to reduce the current. The current goes lower, then the lost volts is going to be lower, so the terminal voltage will actually go up a little bit. So we need to work quickly and make sure you give it time to cool down. Right, let's just choose a different value. Let's go with 7. So 1, 2, 3, 4, 5, 6, 7, something like that. Doesn't have to be exact. Here you go for the second data point. 0.56440, 56440. And I do find speaking out loud helps me, so I make no apologies for that. Choose a different one. 64418. Just like that. Just writing down the numbers as we go along. So 78388. You'll notice that the current is going up, the terminal potential difference is going down. That is because we've got more lost volts. With higher current, there's going to be more lost volts across this internal resistance. I didn't name it. Let's go for this one. 0.99 and 0.9834 something. Oh, I didn't get that. 0.993380. So really go to an extra significant figure then. How about that? So it auto scales on this one, but I've got to write what I've got. So I might have to make a little note here about the fact it auto scales. Otherwise it looks like I'm making stuff up or I haven't recorded the right number of significant figures. So I'm going to put a little note here saying auto scale adjust. Now the other reason why that's important is because if the auto scale is adjusted there, that might mean that the resistance of the voltmeter has changed at that point. So if our results are supposed to show a straight line and we get two different gradient straight lines, that indicates that the load resistance is not what we expect it to be because of this. Now, it shouldn't actually matter for this experiment, actually, but I'll write it down anyway, just in case. Right, let's go for the sixth one. 1242901. I think that was 2901. Yeah. 1.24. That's a lot of numbers for me to hold in my head at once. I am struggling. Let's whack it down to there to get the sixth result. Here we go. 1841563. I think that was about right. Yeah. So there we go. They're the table of results. That's the best I could do. And I could gather more. I can't get repeats of each of these, you can see why, but I could just get more results if I want to plot more points on my graph. But this is only an A-level practical. This is good enough. I could go the opposite direction and reduce this to try and take account of any cooling and have a second set of data where I'm decreasing the current. But all I'm going to end up doing is plotting them on a set of axes. And instead of having 7 points, I'll end up having 14 points. Maybe 13 points if I immediately go back. So there's no point doing that. There's no advantage. Now it's time to process the data. We don't have to do an awful lot of processing. In fact, we don't really have to do any processing at all. We want an equation in the form y equals mx plus c. And we're basically there. Look, v is equal to minus r I plus epsilon is already in the form y equals mx plus c. If I plot this on the y-axis, and this on the x-axis, which is good because current was our independent variable, so I'm glad that's on the x-axis, although that's not a rule. Then that is going to be our gradient, which we can read off the graph. And that is going to be our y-intercept that we can read off the graph. And then we can check those with data for this particular brand of battery, because I ended up changing the battery because the other ones were so bad. Right, let's think of a scale. Let's just draw some axes. Now, I think this is a sensible scale. We're going up here, where every small square is 0.025 amps or 25 milliamps. Really, I should have only written the numbers 0, 0.50, 1.00, 1.50, and 2.00, because you should only really use intervals of 1, 2, or 5, or as a mantissa, so you could go with 0.1, 0.2, or 0.5, or you can go with 10, 20, or 50, but not 25, or 0.25, that's a bit iffy. But I've done it now anyway, so it doesn't really matter. On the y-axis, I'm going up to 5 volts, so this is 1, 2, 3, 4, 5, that's fine. Because we're going from about here-ish to about here-ish, that's just over half the available paper, so that's okay for a vertical scale. And because we're going from around about here-ish to around about here-ish, that's more than half of the paper in the horizontal direction, so that's okay as well. So I'm looking at this table, chose a scale which is as easy to use as possible, and my little pro tip, I've written down the amount that is represented by each small square to help me when I come to plotting. Okay, so let's get plotting. Okay, so there's my first point. Now, an important thing about this, I'm only going to put points on the fine grid lines. You could interpolate. I'm not going to. I don't think there's much point doing that. So you can see 0.48 on the x-axis. Well, if we go from 0.5, 0.48 is 0.02 smaller, but I've got 0.025 per small square. So I've just got one small square below 0.50 and plotted the x there. It could actually be a nudge further over, but to the nearest intersection of fine grid lines, that's the best I'm going to get. And I've done the same thing with the vertical axis. This is 4, that's 4.5, and it's actually 0.08 higher than that. Well, 0.08 on the y-axis, that's just a little bit less than 2 small squares. So I've plotted it 2 small squares up, because that's the nearest place where the fine grid lines cross to the point where that data is. It's close to there. In terms of error bars, I'll worry about that later, whether I can even use error bars with this practical. Let's get all of the data points plotted. So the reason why we can do this is just take the 4th data point, 0.78, and if I divide that by 0.025, that tells me I've got to go just over 32 small squares along. I'll just do 31 small squares along. I'll just go 31 small squares along. We do the same thing for 3.88 divided by 0.05. So that's just over, so it's near enough 78 squares vertically. So I've got to go 31 squares across, small squares across, and 78 squares vertically. So 31 across, 78, 10, 20, 30, 40, 50, 60, 70, 8. That puts the data point there. So it's very, very quick if you use these to work out where you need to put your data points. You don't have to try and guess and count along. It's not difficult. You just do that divided by that divided by that, poof, get it plotted. And there we have it. Took minutes, didn't take long at all using that little pro tip. Right, now where did I put my ruler? There it is. Let's get our line of best fit drawn. So I rotate the page to make it slightly easier, try to line it all up. It's going to be around about there-ish. Before I do that, let's check and see if there's any sensible error bars that we can draw. Well, the uncertainties of these, they were fluctuating a little bit, so I'd have to sort of estimate what those uncertainties were. But if we just go with the uncertainty caused by the resolution of the instrument. So let's work out the greatest one, the one with the greatest uncertainty, that's the first one there, 0.48. So if we say that 0.01 divided by 0.48, that's 2% uncertainty, 2%, which for that particular data point would be less than a small square. about half a small square. So there's no point, and that's the one with the biggest uncertainty. There's no point doing the x uncertainty error bars. Let's just check the y one. So 4.58, so that's 0.01 divided by 0.458. Try again, 4.58. That is the less than 0.2% uncertainty. Well, that's the bigger one down here. So let's go with this one down here. So 0.001, 1.563. Well, that's even smaller. Let's go with this one here. So 0.01, 3.88. It's still less than 0.3%, less than 0.3% uncertainty, which I would not be able to plot error bars for that. The uncertainty is just too small. So there's no point me even considering error bars on these data. Even if I said the uncertainty was twice that, 3 times that, it still wouldn't be enough to draw error bars. So I'm just going to have to wing it, and I don't know, I can't really do an uncertainty evaluation for this practical. I just can't. So let's do our line of best fit. I mean, I suppose I could estimate, I could try and draw a worst acceptable line of best fit without, it's about there-ish, without error bars, but it is just going to be a guess. You know, I might say, well, maybe it could be slightly steeper, but you can see the errors are so tiny, there's no point. There is no point. Right, gradient calculation. I've got my line. My internal resistance is minus the gradient because of the equation I've used. So let's pick some places that are near grid lines. There's one. Come all the way down here. There's another one. Using points on the line as far away as possible. What's the coordinate of this point? This would be 1. Oh, brain's not working. 2 subtract 0.025, 1.975 on the x-axis. On the y-axis, 10, 20, 27 small squares, so it's 27 lots of 0.05. Again, I could possibly do that without a calculator, but my brain is not turned on. There we go. Let's write the coordinates for this point up here. So it's 0.275, 0.275. So it's 0.25 plus that, one of them. And then y-axis, 5.00. Lovely. So the gradient, which is equal to minus r, is going to be the difference in the y-axis. So that is 5.00 subtract 1.35 divided by, and the difference in the x-axis, which is 1.975 subtract 0.275. Notice the mistake I've made. I should have done that, subtract that. I've got that back to front, because I do expect to get a negative number. Okay, so let's chuck this into our calculator. Calculator now. Right, then 1.975 subtract 0.275 divide. So we get negative 2.147, leave it like that. Unit would be ohms, because it's volts per ampere, which is the same thing as ohms. Well, that means that R is equal to -1 times that, which is 2.147 ohms. But that is for 4, let's call them cells. I don't know if they're batteries or cells. Let's call them cells. So our internal resistance is going to be a quarter of that. So R for one cell, let's just call it R0 or something, and I'll label it in a second, is 0.537 ohms. That's for one cell. Now, to get the EMF, what we need to do is get the y-intercept. But look, it goes all the way over here somewhere. I don't know what it is. So what I could do is I could use the equation y equals mx plus c to get the y-intercept. Or, now that I've got this equation, I could just take this value here, plug it back into this equation for that point and or for that point, should be the same, and pull out what epsilon is. It's the same thing. So let's use this point here. Doesn't really matter. Let's use this point. I could use both, of course, and get an uncertainty in epsilon from that, but I just don't think it's worth doing. So let's just use this one here. V was equal to 1.35 volts, and we're going to plus I, which was 1.975 amperes, multiplied by 2.147 ohms for all four resistors, all four cells. Okay, calculator, like this, 1.35, 1.975, 2.147 times add, and we got 5.590, might as well round it to three significant figures because this is three significant figures, volts. And so our epsilon naught, that's for one resistor, is going to be one cell is going to be a quarter of this, which was 1. Was it really as low as that? Well, there we go. 1.398 volts, and that's for one cell. Now, of course, I've got to reference what it should be. That's the tricky bit. So let's go with this off-brand battery now. GP Super. Let's see if we can get any information about GP Super. Nothing says quality video, like reflected lights from over my head. Hopefully you can cope with that. Right, GP Super, alkaline battery, internal resistance D. It's the D size one we want. Or I could even search for, oops, where's it gone? I could even search for LR, is it LR20? LR20. Or I could even search for 0 mercury and cadmium. Well, I'm not going to search what it doesn't have. Energizer. Really? Is that an Energizer battery? GP Industrial. GP Super. GP is a registered trademark, so maybe it's that one. Is there a nice picture of it? Oh, that's a lot of nonsense. Internal. Go find internal resistance. Low internal resistance. Cracking. Can you tell me what it is? No. Right. Impedance. You can't even tell me what the impedance is. Well, that's rubbish. Let's see if I've got another one. Wholesale batteries. That sounds like the sort of thing I would buy. I mean, there's no reason to think that's this. TDR force. Too long didn't read force. Straight from China. Straight from Shanghai. Doesn't tell me internal resistance. Right, so I think I'm going to give up. I'm going to use the Duracell reference that I had. It was all approximate anyway. So I've got the full URL here across the top, so I'm just going to use that. So as always, I don't really want to use a fresh page for this. I'm just going to bang it up there. Perhaps it's not, I should make it flow a bit better. I could have put this up there instead, but it doesn't matter. It's a working document. So according to that, access then internal resistance expected to be less than 1 ohm, measured to be 0.537 ohms. That's it. That's all I have to say. And I can't really do a meaningful error analysis. I could put a statement here about how the uncertainties are too small to be able to draw error bars. I mean, I might even write that on the graph bit there, but otherwise we're done. That is the internal resistance of a battery measured, the internal resistance and EMF of a battery measured. Don't use a power supply for this. Some power supplies do funny things, sort of switched mode power supplies and things like that. You can't always get a sensible number from them. So this is the sort of thing you definitely want to use a battery for. Right, hopefully you found that useful. Stay tuned for another one.